All right, so this is the video for section 3.1, and this is, of course, applied calculus. So we're going to start in chapter 3 with the limit of a function, and then we're sort of going to get into derivatives. So the first thing is I'm going to go through some rules and some definitions. There are not going to be any theoretical definitions of a limit, just obviously this is applied calc for business majors. So we're going to sort of skip over that, if you will. So if we let f be a function, and so by a function we mean f of x, and then we let a and l be real numbers. So what happens is, as the value x, remember, so we have a function f of x. As x takes values that are going to be closer and closer to a on both sides, so we have to think about the left side and the right side. So if I have this function and I'm approaching it from this side and also from the right side, then whatever this value, whatever this x is, let me kind of go here, right? So this will be the value of the limit of the function, if you will. Now, the value of the function f of x will approach, and so this is the function. As x gets closer and closer to a, right? Then the value of the function, if it gets closer and closer or equal to some value L, then the limit of f of x as x approaches a is written as follows. So the limit of f of x as x approaches a is equal to L. And remember, we define a and L to be real numbers and f to be a function. So there are some rules that I'm going to go over, and then I'm going to go ahead and do the exercises for section 3.1. So again, we're going to let a, lowercase a, uppercase a, and b be real numbers. We're also going to define f and g to be functions, such that the limit of f of x as x approaches a is equal to a, and the limit of g of x as x approaches a is equal to b. So the first rule is that if k is a constant, then the limit of k as x approaches a is equal to k. And so the example would be here, if I say the limit of 3 as x approaches 2 is going to be equal to 3, right? Because that's a constant function, and a constant function is just going to be a horizontal line, right? In this case, because since we're talking about f of x. Now also the limit of k times f of x as x approaches a is going to be the same as k times a. So remember, we define the limit of f of x as x approaches lowercase a as being equal to a. And so that just tells us that if I have a constant, I can sort of take the constant out, evaluate the limit, and then put the constant back to finish it off. The second one is that a sum and difference, right? So the limit of f of x plus or minus g of x as x approaches a, that means I can do f of x plus g of x or f of x minus g of x, is equal to the limit of f of x as x approaches a plus or minus the limit of g of x as x approaches a, which then is going to give us a plus or minus b. And the example for that would be something like the limit as x approaches a of 2x squared plus 3x, right? So then that means that I can write this as the limit of 2x squared as x approaches a plus the limit of 3x as x approaches a. And that's what that rule says. Now the third one is the limit of f of x times g of x as x approaches a, then it's equal to the limit of f of x as x approaches a times the limit of g of x as x approaches a, which then is going to be equal to a times b, right? So we define, of course, the limit of f of x as x approaches a to be equal to a, and then the limit of g of x as x approaches a to be equal to some real number b. Number 4 is the limit of f of x divided by g of x as x approaches a. It's just going to be equal to the limit of f of x as x approaches a divided by the limit of g of x as x approaches a. In other words, it's going to be a divided by b if b does not equal 0. Now number 5 if we define p of x to be a polynomial, then the limit of p of x as x approaches a is just equal to p of a. So let me show you an example. If I have the limit of 2x squared as x approaches 1, then that's just going to be equal to 2 times 1 to the second power, which is just 2 times 1, which is just going to be 2. And so in other words, I can just evaluate, right? So if I define p of x to be 2x squared, then the limit is just going to be, in this case, I chose a to be 1. So it's just going to be 2 times 1 to the second power. Number 6, it says for any real number k, again k is a constant, the limit of f of x as x approaches a raised to the k power is just equal to the limit of f of x as x approaches a raised to the k power, right? Provided that the limit exists, in other words, it will be a raised to the k power. Now, number 7, if the limit of f of x as x approaches a is equal to the limit of g of x as x approaches a, if f of x is equal to g of x for all x not equal to a, right? So in other words, if the limit of two functions as x approaches some value are equal to each other, then that means that f of x, the two functions will be equal for all values except a itself. Number 8, for any real number, as long as b is greater than 0, in other words, b is positive, the limit of b raised to the f of x as x approaches a is going to be equal to b being my base, raised to the limit of f of x as x approaches a, which then is going to be equal to the constant b raised to the a power, since we know that the limit of f of x as x approaches a is just equal to a. And this is what I wrote there. So number 9 says for any real number b is between 0 and 1, or b is greater than 1, then the limit of the log base b of f of x as x approaches a is going to be equal to the log base a of the limit of f of x as x approaches a, which then is going to give us just the log base b of a, right? So again, we define the limit of f of x as x approaches lowercase a to be uppercase a, and they're both real numbers. Now, limit at infinity. For any positive number n, the limit of 1 over x to the n power as x approaches infinity is equal to 0. And the limit of 1 over x to the n power as x approaches negative infinity is also equal to 0. Now the second one, if x is less than 0, then x to the n power does not exist for some values of n. So therefore the second limit is undefined for some values of n. So we have to be careful just with this one here if x happens to be negative. All right, so let's look at number 31, right? So number 31 is asking us to find the limit of x squared minus 9 over x minus 3 as x approaches 3. So we know that what I can do here is I can find the limit of x squared minus 9 as x approaches 3 divided by the limit of x minus 3 as x approaches 3. But what happens is that if I plug in 3, I'm going to get 0, right? If I do 3 minus 3, I'm going to get 0, and I cannot divide by 0. So one of the things that we can do is we can try to factor one of the functions, right? And so then at this point in time, I can go ahead and cancel out like terms, right? So I'm going to have the limit as x approaches 3, basically of x plus 3. And of course, x plus 3 is a polynomial, and you know we sort of set this already. And so what we're going to do here, and so there's several ways that we can do that. We can split up x plus 3, but that really doesn't make any sense. And so x plus 3 is a polynomial, which means that it's just going to be 3 plus 3, which is going to be equal to 6. So the limit of x squared minus 9 over x minus 3 as x approaches 3 is equal to 6, right? The other way that we could have done this, which would have been probably a little bit, I mean, I wouldn't do it this way, but we also could have done it this way following some of the rules that we have, right? So then we know that the limit of x as x approaches 3, x right? That's a polynomial. So that's just going to be equal to 3. And of course, we know that the limit of 3 is x approaching 3. That's a constant, and that's going to be equal to whatever that constant is, and it's still going to be 6. So it doesn't matter how we knock those out, right, or how we do them. All right, the next one is number 34. And again, it says that if x approaches negative 3, so the first thing that you should do is you should try to plug in the value, right? Because sometimes it doesn't give you a 0. So if I do negative 3 to the second power, I get 9, right? Minus 3 minus 6. 9 minus 3 is 6. 6 minus 6 is 0. So we cannot plug in the value negative 3. So what we're going to have to do then is we're going to have to try to factor this, right? So the limit, and I'm going to put here, so we know that this is a difference of squares. So it's just going to be x minus 3. X plus 3, and then the denominator is going to factor into x minus 2, x plus 3, right? And so at this point in time, sorry, that's going to be negative 3, not 3, right? So what I'm going to do now is I'm going to cancel the like terms, right, which is x plus 3. Let me write it here. The limit as x approaches negative 3, and so this is going to be x minus 3, x minus 2, right? And since they're both polynomial, right, the f of x will be my numerator, g of x will be my denominator, so I can do negative 3 minus 3, negative 3 minus 2, which is negative 6 over negative 5, which is just going to be 6 over 5, or 6/5, right? So that's how you do number 34. So number 36, again, it says here the limit of x squared minus 3x minus 10 divided by x minus 5 as x approaches 5. Let's evaluate that limit. But if I plug in 5 and then my denominator, I'm going to get 0. So then what I have to do is I have to factor it. So here, I'm going to have, for this one, it's going to be x minus 5 x plus 2 over x minus 5, right? I can cancel out the like terms, which will be the x minus 5. So I end up with just the limit of x plus 2 as x approaches 5, which then is just going to be, since it's a polynomial, I can just go ahead and plug in the value 5 into it. So then the limit of the original function, x squared minus 3x minus 10, as over x minus 5, as x approaches 5, is equal to 7. So in other words, let me just kind of draw out something here real quick, right? So this is my x. I'm going to make this f of x, right? So then I'm going to put 7 right here, so just so we can see it. Now, x plus 2, right? It's going to just be some, actually, sorry, that doesn't go there. What goes there is the 5, and then I'm going to put the 7 over here. And so then what happens here is, I'm going to try to do it this way so we can see a little bit, and this is not an exact draft, right, but still. So what it's saying is that as x is approaching 5 from both sides, then the value of the function is approaching 7. Now, one of the things that I kind of failed to mention is that we can actually evaluate limits from either the left side or the right side. Now, in order, so if the limit of f of x as x approaches a from the left, that's what the minus means, equals the limit of f of x as x approaches a from the right, right? So that's, so what it's telling us is, you know, this is from the right, it's getting smaller, and this is from the left, it's getting larger. And as it's getting closer and closer to 5 for this example, if those two equal to each other, in other words, if they converge on a value, then the limit as x approaches a of f of x exists, right? So the left side limit the left side limit has to equal the right side limit. So that's just a quick example there. All right, so let's look at number 40. Now, there's several ways that we can solve number 40. Perhaps the best way to do it would be to rationalize the numerator, right? So I have the limit as x approaches 36. Obviously, you can see that 36 minus 36 is equal to 0, so I can't just plug in 36, right? So if I multiply by the conjugate, right, of the numerator, so x, the square root of x minus 6 times square root of x plus 6, what's going to happen there is that when I FOIL those, right, what I'm going to get is the following, right? So if I do square root, I'm going to do it here, then I'm going to go ahead and delete it just for the sake of space. If I FOIL this, right? So square root of x times square root of x is x. Square root of x times 6 is 6 square roots of x, right? Negative 6 times square root of x is negative 6 square root of x, and then negative 6 times negative 6 times 6 is negative 36, which will leave us with x minus 36, right? So that's why we did that. And so what I'm going to do now is sort of finish it off. Right, so we know that this is going to be x minus 36. Here we have the x minus 36, but we also have the square root of x plus 6. So then what I can do is I can cancel out an x minus 36, right? So then I end up with 1 over square root of x plus 6. So then the limit of 1 over square root of x plus 6 as x approaches 36 is just going to be equal to 1 over the square root of 36 plus 6, which is just going to be 1 over 12. And so that's how you can solve the limit. You can find the limit of a function that has a radical. Just rationalize either the numerator or the denominator. So let's move on to 43 and 44, which puts us at the limit at infinity. So recall that the limit as x approaches infinity of 1 over the x power is equal to 0. Right? So that's important because that's what we're going to do here. So now when we evaluate the limit infinity at infinity, what we want to do is we want to divide the top and the bottom by the highest power in the denominator. So then what happens is here I get, if I do that, I'm going to get 3x over x, 7x over x minus 1 over x. So since the degree of my denominator was 1, so then I'm just going to go ahead and divide by x. Now, what we really are doing here is we are finding the derivative of 3x over x, right? Now, I'm not going to require you to write all this out, but I just want you to understand that this is in reality what we're doing, right? And so, of course, I might have to move 45 down a little bit or just delete some of these. So then I'm going to go back and I'm going to go ahead and put it this way. So 3x over x is just going to be 3. 7x over x is just going to be 7. And then this is just going to be 1 over x. So what happens with 43 is that we know that the limit of 1 over x as x approaches infinity is equal to 0. So then this is going to be equal to 3 over 7 minus 0, which is just going to be 3 sevenths. And so those obviously have to agree, right? I'm going to, for the sake of space, leave this one for you guys for extra so you guys can sort of get that one done just for the sake of space here real quick. All right, number 45, we have the limit of 3x squared plus 2x divided by 2x squared minus 2x plus 1 as x approaches negative infinity. So what we're going to do is we're going to divide everything by the highest power in the denominator, which will be x squared plus 2x over x squared, and then 2x squared over x squared minus 2x over x squared plus 1 over x squared, right? So we divided everything by the highest power in the denominator. We can clean this up a little bit. So this is the limit as x approaches negative infinity. And so what's going to happen here, I'm going to have a 3. And then here, I'm going to end up with a 2 over x. That's going to be a 2. That's going to be a 2 over x. And then that's just going to be a 1 over x squared. So if we remember the rule for this, we know that the limit of 2 over x as x approaches negative infinity is going to be 0, right? And so I'm going to have here, let me just do it this way. So 3 minus 0, 2 minus 0 plus 0 is just going to give me 3 halves, right? Because we know that this one and these two are just going to be equal to 0, right? In other words, so what happens is that as x gets larger and larger, right? So if I do 1 over 6, right, that's going to be a value that we can easily evaluate, right? So 1 over 6 is just going to be like 0.16 or something. If I do 1 over 20, right, now I get 0.05. So remember, what I'm doing here is I'm just showing that x is getting larger and larger and larger. So if I do 1 over 100, right, now I'm at 0.01. But what about if I do 1 over 10,000? Right, so I do 1 divided by 10,000. So now that's going to be equal to 0.0001. And you can imagine what happens when I divide it by a million, right? And then that's going to be what is it, 5 zeros? 1, 2, 3, 4, 5, that. So you can see how the value is getting smaller and smaller and smaller as x gets larger and larger and larger. So that's why it's equal to 0. All right, let's do number 49. So number 49 is the same thing, right? We're going to go ahead and divide by the highest power in the denominator. So that's the limit as x approaches infinity of 2x to the third over x squared minus x over x squared minus 3 over x squared, and then 6x squared over x squared minus x over x squared minus 1 over x squared. And I can clean this up a little bit. So it's going to be limit as x approaches infinity of 2x minus 1 over x minus 3 over x squared, and then 6 minus 1 over x minus 1 over x squared. So just going back to what we had done in the previous examples, here what's going to happen is the following, right? So now I end up with the limit as x approaches infinity of 2x, right, minus 0 here, right? 6 minus 0 minus 0. Now, if you think about this for a second, as x gets larger and larger and larger and larger, so if you can imagine, what we're really doing is we are dividing a larger and larger value by 6, right? And so just for example, if I show you the same thing here that I had done, right? So let's say x is equal to 20, right? So then I got 40 over 6. Right, 40 over 6, so I get about 6.67. But what happens when x is equal to 1,000, right? So now I got 2,000 over 6, right? And I get 333.33 or something like that. So you can see that it's just getting larger and larger and larger. So this is equal to infinity, which means that the limit does not exist. All right, let's go to 53. So 53, what we have here is we have a piecewise defined function, right? So let f of x be defined as the following. If x to the third power plus 2, if x does not equal negative 1. Now, and let me just make sure that I wrote this one right for 53 before I get started. Let me just double check it here real quick. I gotta go back one more page, sorry. All right, 53. As x approaches negative 1. Okay, I got that one right. All right, I'm gonna go back here because I'm gonna go back to the page for some of the other ones. So for number 53, what happens is the following. We can go ahead and say, okay, so what happens here, all right, I'm sorry, I gotta go back because this is not, I wanna make sure I wrote this correctly and not switched up some values. Yeah, okay. So what we have here is that when x is equal to negative 5, x is equal to negative 1, the value of the function is equal to 5. But if we look at x to the third power, right? And I say, okay, so what's the limit of x squared plus 2 as x approaches negative 1? So that's just going to be negative 1 to the third power plus 2, which is equal to 1, right? So if I approach it from the left, right, that means I'm getting closer and closer and closer to negative 1 from the left, right? So here's my negative 1, right? I'm plugging in, of course, this is x is equal to negative 1. I'm getting closer and closer to negative 1 from the left. Now, here's the deal. We know that if x is equal to negative 1, then the limit is going to be 5. But what happens is I get closer and closer to negative 1. What happens is that it jumps, right? So I'm getting closer to some value 1, right here. But when it's actually equal to negative 1, it's actually, the function is actually equal to 5. But I can evaluate it from both sides, right? So what happens when I evaluate it from the right, it equals to 1. So therefore, for this particular function, the limit as x approaches negative 1 of the function f of x is equal to 1, since the left side is equal to the right side, right? Even though we define this piece right here, because it's just approaching the value 1 from both sides, and then of course it can't equal negative 1, so it jumps up to 5. All right, let's look at number 87 here real quick. I think I already gave you guys an extra credit one, so just make sure you double check that one and just submit it. I did create a Dropbox. So for number 87, let me go back to that page in the textbook. All right, where you at? Okay. It says the cost in dollars for manufacturing a particular DVD is given by C of x is equal to 15,000 plus 6x. So x is the number of DVDs produced. Now, recall from the previous chapter that the average cost per DVD is defined as C bar of x is just the cost function divided by the number of units, right? So then what they're asking us is, they're asking us to find the limit of C bar of x as x approaches infinity, right? And so we know then that the average cost function is going to be, right, 15,000 plus 6x over x, right? That's C bar of x. We divide that by x, which means that I end up with this, right, over x plus 6. If I kind of clean this up a little bit, this is what I end up with, right, for number 87. So then, if I evaluate the limit, we know that the limit of 15,000 over x as x approaches infinity is going to be 0. And so the answer to this one is 6. So what does this mean? It means that the average cost is going to approach $6 as the number of DVDs produced become very large. So then, in other words, the cheapest amount, the most inexpensive amount that this company can produce of DVDs, regardless of how many, right? If you just produce 1 million of them or 2 million, it's going to be $6. So it's never going to go below $6 for this particular example. The next one is number 89, and what I'm going to do for number 89 is, let me just go ahead and knock this out for you guys. So number 89. So it says a company training program has determined that on average, a new employee produces P of X items per day after S days of on-the-job training. And they define P of S to be 63S over S plus 8. So then what they're asking us is find the limit of P of S as X approaches infinity. So if we do that, then this is going to be equal, right? I'm going to write it here. S plus 8. And so what's going to happen here is I'm going to divide everything by the highest power in the denominator, which is going to be S. S over 8, S over S, and S over 8, right? So then this is going to be the limit as x approaches infinity of 63 and then 8 plus x, right? And that's number 89. So we can clearly see that what's going to happen is when I evaluate this, that's going to be 63 over 1 plus 0, which is going to be 63. So what does that mean? That means that the number of items of work that a new employee produces gets closer and closer to 63 as the number of days of training days increases. In other words, no matter how long the employee's been working, at a maximum for this problem, they can produce 63 items, whatever those items are. And that's the end of 3.1. Thank you.